Today's experimental math seminar is the soon to be doctor, already defended, and soon to be get a diploma, AJ Boo, will talk about lattice paths and counting them. Thank you.
So let me share my presentation. Hopefully you can all see it. Can you see it? Okay, cool.
Yes, very well.
Okay, so I'm gonna apologize to those of you who were at my defense because this might be a little repetitive because this is one of the topics that I talked about. But I'm gonna talk about studying the area under generalized Dyck paths. But okay, yeah. So before we go into generalized Dyck paths, let's talk about two well-known types of paths, which are the Dyck and the Motzkin paths. So a Motzkin path of length n is going to be a path in the xy plane from the origin to n0 with steps in 1, 1, 1, 0, 1, -1, and that never goes below the x-axis. So we're going to call 1, 1 an upstep.
Can hear you. AJ, can hear you. Are you trying to talk? Robert, can you tell her?
I think she knows.
Okay.
Okay, does this work? I changed my microphone.
Yeah, perfect, perfect.
I don't know when that cut off, but yeah, so we're gonna let 1, 1 be an upstep, right? Because you're going up 1 unit and denote it with a U. 1, 0 be a flat step and denote it with an F because you're just going horizontally, and 1, -1 be a down step because you're going down 1 unit, and we're gonna denote it with AD. And then the Dyck paths are similar, except they're going to avoid these flat steps, right? So for the Motzkin paths, we're going to have n of the steps in this step, in this set, and we're always going to have the same number of up steps as down steps so that we start and end at height 0. And at any point, we're going to have at least as many up steps preceding it as down steps to avoid that negative height. And same with Dyck paths, except we're not going to have that step for Dyck paths. Okay. So this is an example of a Motzkin path of length 10. So it's going to go up 1, then it's flat, then down 1, up 1, down 1, flat, down 1, down 1. So that's an example of what a Motzkin path might look like. Yeah. So now that we got those basic definitions down, before we talk about area, let's talk about just enumerating these paths. So to enumerate paths, we're going to use the following weight enumerators. P of t is equal to the sum over all the paths in P. So in this case, all of the Motzkin paths of t to the power, raised to the power of the length of that path. So for Motzkin paths, we're going to get that P of t is equal to 1 plus Tp of t plus t squared P of t squared. And to prove this, we're going to let P denote the set of all of the Motzkin paths. And then we're going to have that P is generated by P equals the empty path union FP union UPDP. And that's because for the Motzkin paths, right, we can have an empty path. But if it's not empty, it's going to have to either start with a flat step or an up step because we can't start with a down step because that will give us negative height. If it starts with a flat step, then whatever follows is going to be a path that starts and ends at height 0 and never goes below the x-axis, because if it goes below the x-axis, then the overall path does as well. And so it's going to have to be a Motzkin path, right? If it starts with an up step, we're going to let this D denote the down step that brings us back to the x-axis for the first time, because we have to return to height 0 if we're going to end at height 0. And then whatever happens after that down step starts and ends at height 0. So that has to be a Motzkin path. And then whatever happens in between those up and down steps, right? We're starting and ending at height 1. And the way that we define this D, we know that we have to stay above or at least at height 1, right? So whatever happens here has to be a Motzkin path shifted up height 1. So that's how we get that grammar. And then turning this into the numerator, we're going to take each of these steps and turn it into a T, right? So we're going to get P equals 1, because the empty path has length 0, obviously, plus T from that F times P, plus T squared, so that's from the U and the D, times P squared. And that's going to give us the desired equation. Okay. So what if we want to keep track of the area as well? So to keep track of the area, we're going to now use a bivariate weight enumerator P of TQ, where now we are taking the sum over all the paths of T raised to the power of the length of W, right? So that stays the same. But now we're also going to have Q raised to the power of the area under W. So for example, the Motzkin path UD is going to have weight T to the 4th Q squared, right? Because there are 4 steps and each of these areas are 1. So the total area is going to be 2. UFFD is going to have weight T to the 4th Q cubed, right? Because there are 4 steps. So it's going to give us a T to the 4th. And the area underneath is 3. So it gives us Q cubed. And then FFFF is going to have weight T to the 4th, right? Because there are 4 steps, but there's no area underneath. So that kind of introduces what the areas will be. Okay, so now that we have that, let's go back to what we talked about with the Motzkin paths, where we got this grammar and adjust it for area. So note that in these 2 cases, we're not going to have to do any sort of adjustment for the area, right? Because the empty path is going to have area 0. So its weight is still going to be 1. And then for a Motzkin path of the form FP, right, we can write it as M equals F M sub 0. And since we're starting and ending at height 0, and this F doesn't have any area underneath it, the area under M and M sub 0 are going to be the same. Okay. But when we look at this final case, we're going to have to make some adjustments for the area. So if we have a Motzkin path that's written as M equals U, M sub 1, D, M sub 0, right, then we're going to first look at the area under the U and the D, right? And so that's going to give us a total area of 1. And then for M0, we're not going to have to make any adjustments for the area since we're starting and ending at height 0. So that the area under the M sub 0 is going to be equal to the area under the portion of the Motzkin path that it represents. And then for this M sub 1, though, we're adjusted up 1 unit, right? So every step in M sub 1 is going to have 1 more unit block below it than is like represented in the way that we write M sub 1. Okay, so to adjust for that, what we're going to have is M of TQ is equal to 1, so that's the weight of the empty path, plus TM of TQ, so that's for FP, because there's no adjustments to area, plus T squared Q, so that's the up and down step is 2 steps, so that gives us T squared, and the total area underneath is 1, so that gives us Q, times M of TQ, so that's for the area under all the possible M sub 0s, times M of QTQ, so that's going to be the area under all of the possible M sub 1s. Okay, so that is an example of how to get that equation for the Motzkin paths. Now that we've talked about the, I guess, more well-known examples of generalized Dyck path, let's talk about what a generalized Dyck path is. So a generalized Dyck path is a path in the XY plane from the origin to N0 with an arbitrary set of atomic steps that never goes below the x-axis. So Dyck and Matzian paths are obviously examples of generalized Dyck paths, right? But our set of steps is 1, 1, 1, 0, and 1, -1. But now we can go up and down by more than 1 unit if we want, for example. So this is an example of a generalized Dyck path with, with steps given by the set 1, 2, -1, -2. An example of a path would be going up 1 unit, then going up 2 units, going down 2 units, going up 2 units, going up 1 unit, going down 2 units, and then going down 2 units. So that is an example of a generalized Dyck path with steps given by the set. Okay. So now that we have that, I'm going to talk a little bit about my joint work with Doron Zeilberger, and this is covered in our joint paper, using symbolic computation to explore generalized Dyck paths and their areas, which can be found on arXiv. And it has an accompanying Maple package, ddw.txt. And the link to this Maple package is found in our paper, but it's also posted on both of our websites. And what this project covered was first using symbolic programming to generate f of tx such that f of t p is equal to 0, where p of t is the weight enumerator for the generalized Dyck paths with steps in a given set S. And then we're going to extend it to keep track of area as well. So first I'm going to go over how to do this first one, so that we have a general idea, and then talk about how to adjust it. So an example of an output, right, would be if we're looking at the generalized Dyck path with steps given by the set 1, 2, -1, -2, we can use our Maple procedure EQGFT, and it will give us something that looks like this. So that's going to be what the output looks like. Okay. So now that, before we go into the process, I want to introduce some notation that we're going to be using. So we're going to let P sub AB be the set of generalized Dyck paths with a given set of steps. And it's going to start at height A and end at height B. And P sub AB of T is going to be its weight enumerator. And then we're going to separate the subset of the paths that stay strictly above the x-axis, except for at an endpoint if one of the endpoints is 0, because then it obviously has to hit 0 at that point. And we're going to denote this subset with Q sub AB, and its enumerator is going to be Q sub AB of T. Okay, so now that we got that notation, let's talk about how we're going to go about enumerating these paths. So the general idea is we're going to begin with P sub 0, 0, right? Because that's going to be the actual family that we want to find, because our paths should start and end at height 0. And then we're going to get some new equations and variables by breaking the paths down into a concatenation of legal steps and subpaths with various starting and ending heights. And we're going to use the enumerating function for each of these children to get the enumerator for the original set. And sometimes we'll replace one of these child sets with one that has the same number of elements but is easier to work with, which we'll see later. And we're going to continue and repeat this process with each child set until no more children are produced. So then we're going to have an equation for each of these families of paths. And then we're going to assign different variables to each of these sets, and that's going to give us our system of equations. And we're going to use Grosvenor bases to get the, equation satisfied by P of T. Yeah. So for those of you who haven't seen Grosvenor bases before, I'm just going to quickly go over the definition and not really go into that many details about it. But a Grosvenor basis of an ideal in a polynomial ring over a field is a finite subset of that ideal, such that every non-zero polynomial in the ideal is going to be divisible by the leading term of one of the elements in the Grosvenor basis. So a Grosvenor basis, it's helpful because it simplifies solving the ideal membership problem and finding solutions to a system of polynomial equations, which is why we're going to use them. And specifically, there's a fact that a polynomial f lies in the ideal with Grosvenor basis g if and only if the remainder on division of f by g is 0. Okay, so that's all I'm going to say about Grosvenor bases, just so that you kind of have an idea of what they are and why we're using them. So now let's talk about our process for finding our PABs and GABs. So we'll do an example with P sub 0, 0 of t. So we want to start and end at height 0, right? And we're going to suppose that we're allowed to take a flat step. So 0 is in our set S. So we could have the empty path. Or one possibility is that we begin with the flat step and then we can write our path as FP sub 0, 0, right? Because the flat step is not doing any sort of adjustment to our height or anything. So we're still going to start and end at height 0. Otherwise, we're going to have to begin with a positive step, right? Because we can't start with a negative step because then we'd have negative height. And therefore, the path must return to the x-axis for the first time. You know this because we end at height 0, right? So we got to hit height 0 again. So we're going to split our path into two subpaths at this point and write it as Q00, P00, right? So everything here is going to be up until the point that we hit the x-axis for the first time, and then whatever follows. And if it only hits the x-axis once, right, that's fine because our set P00 contains the empty path. So then here we just have the empty path. So this is kind of similar to like how we defined the D before in our well, when we were proving the Motzkin path equation. Okay, so that's going to give us that P sub 0, 0 is equal to the union of these three sets, right? So it's going to be empty path union FP00 union Q00 P00. And that's going to give us the equation P00 is equal to 1, because that's going to be the weight of the empty path since it has length 0, plus T from the flat step times P00 plus Q00 times P00. So we're just replacing each of these with its weight numerator. But now, right, we have this Q00 and Q00 that was not there before. So we're going to have to do something about the same process, but for those Q00s. Okay. So before we go into how to do that, let's introduce some more notation. So we're going to let U be the set that gives the legal upward steps and D be the set that gives the legal downward steps. So for example, in our set S equals 1, 2, -1, -2, we have the following legal steps. So for up steps, we can either go up 1 unit, so we'll denote that U1, or we can go up 2 units, which will denote U2, and that gives us U is equal to 1 or 2, because that's the amount that we can go up by. For down steps, we can go down 1 unit, which will denote D1, or down 2 units, which will denote D2. So our D is also going to be equal to 1 or 2, because that's the number of units that we can go down by in a single step. Okay, so now that we have that notation, what we're going to do is we're going to note that the legal initial steps are going to be the U sub K, such that K is in U, right? Because in other words, this is all of the possible positive steps, because our initial step has to be positive. And then if we were to remove that first step, what we're left from our overall path, what we're left with is a path that starts at height K, right? Because that UK is going to take us up to height K. So once we take that away, we're starting at that height. And then the legal final steps are going to be D sub L, such that L is in D. In other words, all of the possible downward steps. And separating this step leaves a path that ends at height L, right? Because we're going from, our final step is taking us down L units and ending at height 0. So therefore, before that step, we must be at height L. So that's going to give us that Q sub 0, 0 is equal to the union over all K and U's and all L's and D's of U sub K, Q sub KL, D sub L. So basically all of the possible first and last steps, and then whatever has to happen in between. And then we're going to note that we can shift each of these paths down by 1 unit to create a bijection with P sub K minus 1, L minus 1, right? Because the way that Q is defined, we know that we're going to be at least at height 1. So we're allowed to do this shift in height and still get an element of P sub K minus 1, L minus 1. Okay. And so putting that all together, what we're going to get is that Q sub 0, 0 of T is equal to T squared. So that's from these two steps times the sum over all K and U and L and D of the weight enumerator of this set, because that's going to be equal to the weight enumerator of Q sub K L. So it's going to be P sub K minus 1, L minus 1 of T. So that's going to be an example of how we get our Q sub 0, 0s. Okay, yeah, so let's like show this process, but with the example we've been using of the generalized Dyck paths with steps given by 1, 2, -1, -2. So we already talked about how our set U is going to be equal to 1, 2, and our set D is also 1, 2. So the possible initial steps are U1, right? So to go up 1 unit, or U2 to go up 2 units. So therefore, that gives us that Q 0, 0 is either going to start with the step that goes up 1 unit, and then whatever follows is going to start at height 1, or it's going to start with U2, and then whatever follows is going to start at height 2. And then our legal final steps are D1, which goes down 1 unit, or D2, which goes down 2 units, right? So for each of these, we're just going to take the possible last steps and separate them, right? So if D1 is our last step, we're going to end at height 1. And if D2 is our last step, we're going to end at height 2, right? So we're going to get this. So that's going to tell us that Q sub 0, 0 is equal to T squared times Q11 plus T squared times Q12 plus T squared times Q21 plus T squared times Q22. But we don't want to work with these Qs, right? So we're going to create the bijection with the paths that can go to height 0, and we're going to shift everything down by 1 unit, right? So then putting that together, we're going to get that Q sub 0, 0 is equal to T squared times P sub 0, 0 plus T squared times P sub 0, 1 plus T squared times P sub 1, 0 plus T squared times P sub 1, 1. So that would be this process for that family of generalized Dyck paths. Okay. And then we're going to keep doing this until we have no more children. So our procedure make syst can be used to get our system of equations. So for example, for this this set of generalized Dyck paths, we're going to get this system of equations, right? And note that for each of the variables that appears, we have an equation that is equal to. And then once we have this system of equations, we can use Grosvenor bases to solve, or to get the polynomial, or the f of tx, I think is what I called it, that's satisfied by our P sub 0, 0, which is our enumerator for the family of generalized Dyck paths. Okay, so now that we talked about just enumerating them, let's talk about extending this to area. So we can modify this method to keep track of the area as well. So for example, before, this is what we had in our slide where we talked about finding the Q sub 0, 0s. But if we want to consider area, right? So we still have the T squared from the U sub K and D sub L, because it's still 2 steps. But we have to think about the area under those 2 steps, right? So under U sub K, is going to be the area K over 2, because it's just a triangle with like base 1 and height K. And then D sub L is going to have area L over 2, right? So that's going to give us this Q to the power of K over 2 plus L over 2. And then since we did that shift of moving everything down by 1 unit, we're going to have to add a unit block beneath each step. So we're going to have now P sub K minus 1, L minus 1 of QT, Q, instead of just T. Yeah. So going back to the example that we've been doing of 1, 2, -1, -2, right? This is what we had in our example for what we got for Q sub 0, 0. So here we're going to note that the area under our U1s and the area under the D1, they're both going to be equal to 1/2, right? And the area under the steps U2 and D2 are both going to be 1. Okay, so that's going to give us this equation, right? So for example, looking at this first part, right? The U1 and D1 is going to give us a total area of 1. So it's going to give us QT squared because it's 2 steps. And then since we shifted down a unit, we have to do P00 of QTQ. And then for this part, right, our U1 and D2 is still 2 steps, but now it has a total area of 3/2. So we're going to have Q to the 3/2 times T squared. And then again, we're going to have to take P01 of QT because we did that shift in the height, Q. And then we're going to do like the same thing for these cases. And that's how we get this equation and adjust for the change in heights. Okay. So, oops. An example of our output would be, so if we use our procedure Q makes syst, we can get this system of functional equations, and it's going to look something like this. Right, so we still have the same number of equations. The output is like somewhat similar to what we had before, right? We just have the adjustments for the changes in the areas. Yeah, but then we need to think about how we get from this to the actual expression that we want, right? So after we find the system of functional equations, we're going to have the computer find a system of algebraic equations for each of the components, P sub AB and Q sub AB. So to do this, we're going to use 2 things. One is the Taylor series expansion about Q equals 1. So that's going to tell us, right, that P sub AB of TQ is going to be equal to the sum from 0 to infinity of 1 over n factorial times the derivative, the nth derivative with respect to Q of P sub AB TQ evaluated at Q equals 1 times Q minus 1 raised to the nth power. And that's just the definition of a Taylor series. And then we're also going to use the following lemma. If f of t is a form of power series of a single variable t and q is another variable, then f of qt is equal to the sum from 0 to infinity of 1 over n factorial times the nth derivative with respect to t of f of t times q minus 1 to the n. Okay, so we're going to let p prime sub ab of t1 denote the derivative of p sub ab with respect to q evaluated at q equals 1. That means that p prime of t1 is going to give us the generating function for the sum of the areas of all legal walks of length n, right? So we're going to rewrite all of our p sub ab's and q sub ab's as, so like p sub ab of tq is equal to p sub ab of t1 plus q minus 1 times p prime sub ab of t1 plus higher powers of q minus 1. Great. And this is just using that the Taylor series, and we're going to do the same thing for our q's. And then we're going to expand in powers of q minus 1 and collect our terms. And once we do that, we can use lemma from the previous slide to get more equations by differentiating with respect to t, each of these equations using implicit differentiation. So, for example, again, our set of steps being 1, 2, -1, -2, we can use our procedure Q, EQ, G of t, and we're going to get this output. And that would be an example of an output. Okay. So now
you get a certain sequence. Is that sequence into IIS?
I don't know if this one is.
If not, it should be. Okay.
Okay. Yeah, I can check. I can check later.
Okay.
Yeah, I don't know. Okay, so now let's say that we have the equation PTQ equals FTQ plus G of TQ times P of TQ plus H of TQ times P of TQ times P of QTQ. And we're given what the F, G, and H are. So we can solve for P prime T1, which is, again, going to give us the total area under the passive length n. So note that rather than outputting algebraic equations, which is what we were outputting earlier, we now are going to produce closed form expressions in terms of the radicals, And then we can also solve for higher order derivatives, which we're going to note with pk T1, which is going to be the kth derivative with respect to Q of P of TQ evaluated at Q equals 1. Okay. So the method to do this is described in my paper, Explicit Generating Functions for the Sum of Areas under Dyck and Motzkin paths and for their powers, which is posted on arXiv as well as my website. And it has an accompanying maple package qew.txt, which is linked to in the paper, and it's also found on my website. So a brief description of the process of how we go about finding our desired, derivative is first we're going to plug in Q equals 1, and that's going to allow us to solve for P of T1. And then we're going to use the Taylor series about Q equals 1 and compare the coefficients of Q minus 1 to the n to solve for Pn of T1, so the nth derivative. Okay, so what we're going to end up doing when we look at the coefficients of Q minus 1 to the n is this is going to allow us to express the nth derivative of P with respect to Q evaluated at Q equals 1 as the sum of the derivatives of basically lower order derivatives evaluated at Q equals 1, as well as derivatives of functions of T with respect to T. But since we already solved for our P of T1, we can simply compute any order derivative with respect to T, because now it's just a function with variable T. And then we can also solve for our P prime of, this should be a T, of T1. So what we're going to do is we're going to start with like the first derivative and then work our way, this should be a P, sorry, and work our way up to get the nth derivative, because we're going to have to use those lower order derivatives to find our nth derivative. So let's describe this process with the Motzkin path, since it's kind of hard to explain theoretically, I guess, or like without doing an example. So we already showed that the Motzkin path has the equation m of tq is equal to 1 plus t times m of tq plus t squared q m of qtq times m of tq. So plugging in q equals 1, we get that m of t1 is equal to 1 plus t m of t1 plus t squared m of t1 squared. And then we can solve for m of t1, right? And we're going to get that is equal to 1 minus t plus or minus the square root of negative 3t squared minus 2t plus 1 over 2t squared. Okay, and then this, right, m of t1 should be the weight enumerator for, or it should enumerate all the Motzkin paths of length n, right? So it should have a Taylor series about t equals, yeah, so it should have a Taylor series. And then, so to do that, so only one of these solutions will have a Taylor series, and that's going to be when this is a minus sign, right? So we know that this is going to end up being what our M of T1 has to be, because we know that it has to have that Taylor series expansion. Okay, so doing this process, right? We are going to rewrite everything with its Taylor series about Q minus 1. So that's just what we're doing here. We're just replacing everything with its Taylor series about Q minus 1. And then if we look at the coefficient of Q minus 1 on both sides, what we're going to get is that M sub Q of T1 is equal to T M sub Q of T1 plus T squared times M of T1 times T M sub T of T1 plus 2 M sub Q of T1 plus M T1, M of T1. And then from here, we're going to isolate that M sub Q because that's what we want to solve for, right? And we're going to end up with this fraction. Okay, so now that we have that, we're going to note that we already solved for M of T1, right? So, and then we can solve for M sub T of T1 just by taking the derivative with respect to T. And then if we plug those in, we'll get our desired M sub Q of T1. So what we're going to end up with is T minus 1 plus the square root of negative 3t squared minus 2t plus 1 quantity squared over 4t squared times negative 3t squared minus 2t minus 1. Okay. And then to find the nth derivative, we're going to just repeat this process for all k less than or equal to n and work our way up to the nth derivative. Okay, so now that we have these derivatives, we can look at the Maclaurin series for these functions and get some information about our paths. So for example, M of T1 is going to give us the weight enumerator of the Motzkin paths of length n, right? And so we're going to have this Maclaurin series. M sub Q of T1 is going to give us the weight enumerator of the total area under all Motzkin paths of length n. So for example, we're going to get this Maclaurin series, and this tells us that the total area under all Motzkin paths of length 6 is going to be 190, for example. And then M sub QQ of T1 plus M sub T1 is going to give us the weight enumerator for the sum of the squares of the areas of Motzkin paths of length n, right? So if we square the area of every Motzkin path of length n, or I guess of length, I don't know, 5, we're going to get a total of 198, for example. And then we can also do this for higher powers of this area. So we could do like the sum of the cubes of the areas of Motzkin paths and so on. So one thing that this allows us to study is the average areas and the variance, right? So if we have a family of generalized Dyck paths, right, and we let A sub 0 of n be the number of paths of length n, A sub 1 of n be the total area under such paths of length n, and A sub 2 of n be the sum of the squares of the areas under such paths of length n, then using the Maple package that accompanies our paper, or the paper, we can generate 10,000 or more terms of the sequences of the average area. So it's going to be A sub 1 of n over A sub 0 of n, right? Because that's the total area over the number of paths. And we can also find, for example, the variance. So that's going to be given by A sub 2 of n over A sub 0 of n minus A sub 1 of n over A sub 0 of n quantity squared. And that's like one way that we can do further studies. I ended earlier than I meant to. I was so afraid of going over.
Yeah, but you did a great job explaining it, very, very clear and lucid with
Yeah.
explicit examples.
Well, which means we have time for questions, right? Can I ask a question?
Yeah, go ahead. We have time for questions. Go ahead,
Yeah,
Yusuf.
yeah, you mentioned that you can solve all those equations and radicals, but that's for particular set S, right? Because you have second degree.
So for I guess which method? The first method that I described, yeah, you need the set of steps S. For the second method, you need the equation that the generating function satisfies.
No, I mean, you mentioned that you can solve algebraic equation and radicals. Why is that? Why it's always possible?
Because it's quadratic, and in
Because it's
principle,
quadratic, but
you
it
can
is
do it for
quadratic
cubic and
because of
quadratic.
it's quadratic because of your allowed path. So if you have path 5, you will have quintic.
Yeah, of course. This particular technique is only applicable up to quartic equations, and it's only useful if it's quadratic equations. But it's already very interesting. All the classical paths, Dyck and Motzkin, have quadratic generating functions for the straight enumeration. So, and
So,
this using
this explains, right? So there is something with those paths that is always quadratic. So you do not expect
the previous
do not
part of the talk
expect
was
generating
general.
function higher degree. Or if they are higher degree, they might be factored into quadratic and linear.
Right. The previous part of the talk was completely general, and then algebraic equations. But what's nice, you can specialize and get much more useful and explicit generating functions in terms of radicals for these special cases of Dyck and Motzkin, and even more generalized one, where it has to be quadratic. Yeah. Oh, cubic.
Sorry for my curiosity, but if you don't have quadratic, you can still do it explicitly, right? Implicitly, you can do implicit.
Yeah, of course, yeah.
It's just larger intermediate expression. It's
yes,
right.
Yeah, good point.
Huge,
yeah. So AJ, I have a question. So the sum of the squares you put in the RIS, right?
Yeah, but I need to make. They asked me to make some edits that I did not finish. I had started doing them and then I resubmitted it, and then I was asked to make more edits, but then it was too close to my defense. So I didn't make them, and so because I was focusing on preparing for my defense.
So it's still pending.
So it's still pending, yeah. But now that I've defended, I can finish, fixing everything.
Yeah, it'd be nice if you also put the sum of the cubes.
Yeah, I think I had submitted the sum of the squares and the cubes.
Ah, okay. That'd be nice.
Yeah, it's also interesting. We see this line, the average areas, right? You have a sequence. So how does it look like? Is it large, or how does it grow, average area? It's about linear growth or quadratic, or what is it?
Yeah, remember
I don't remember. I remember we looked at it, but I don't remember what it ended up looking like.
N to the power 3/2, n to the power 1.5 times some constant, that's asymptotics, for the average area, if I remember correctly.
N to the power of
1.5.
1.5, okay.
Times some constant that you can estimate. You can probably do the exact asymptotics also. It would follow probably from the explicit expressions. If you bother, you can probably get the exact the closed form asymptotics in terms of pi and whatever.
Okay.
But it's always n to the power 3/2 for the average. And for the variance, I don't remember, also you can get asymptotics.
You sure, Doron, it's 1.5, not golden ratio? Maybe it's
no, the exponent. The exponent is always rational. No. The stuff in the front could be good, but the exponent is always rational. This, I think, is the theorem.
Oh, okay.
More questions to AJ or me? Well, thanks so much, AJ, for a very illuminating and crystal clear talk. We're going to take a break of 3 weeks, then because it's spring break. So the next talk is in 3 weeks. Thanks so much. And one of the talks is by using Zima. Thanks so much. And
Thank you.
have a great spring break. Thanks for coming.
Okay.
And
Bye,
bye-bye.
everyone. Have a good break.
Thank you.